So we're going to study the linear model in the context of three types of learning problems, not specifically related to the linear model per se. They are sort of general types of machine learning problems, and we'll illustrate these problems for the credit application. Okay, so you're doing credit analysis. Okay, and your client says, just tell me approve or not. Should I give the guy credit or not? Okay, so that's one kind of problem. Let's call that approve or reject. Okay. And another kind of problem that the client might say is, don't tell me approve or not, just tell me the credit level. How much credit should I extend? Okay, so credit level. Credit level. Okay, so that's a different kind of problem. Okay, different from approve or not, and we'll see what exactly is the difference. And then one final type of problem is, the client says, don't tell me what to do. You just give me a probability. So were I to, let's say, give this guy credit, what are the chances they will default? Okay, so the client is asking for a probability of, let's say, default. And you can see these are sort of three distinct types of problems in that the client is asking you to sort of give them different types of information about the input object, in this case an applicant. Okay, now we call this approval reject, and that's what we have focused on so far, classification. Okay, so this is classification. Okay, and what makes it classification is that you're asked to take the input, the applicant, and classify the applicant into a set of different classes. In this case, there's the approve or reject class. Okay, and that's easy to sort of encode in the output variable y, which must be either -1 or +1. Okay, so let that be the mathematical definition of classification. The desired output is -1 or +1. Now we can extend this to multi-class classification, where you have more than two classes. Okay, and we'll see an example of that today, actually. Okay. Credit level. So what distinguishes the credit level from classification is you're not asked for a plus or -1 output. The credit level can be any real number. So in this case, the output, so what's different? The output y can be any real number. Okay, and that real number is supposed to correspond to the credit level. Okay, well, we call this type of output regression. Okay, so the first approve or reject problem, we call it a classification problem. When the desired output is a real value, for example, the credit level, we call it a regression problem. Okay, and so what's different between a regression problem and a probability of default? Okay, is that, well, the output here is also a real number, okay, but it turns out that it has to be between 0 and 1 because that's the definition of a probability. So probabilities are between 0 and 1. 0 chances of happening, 100% chance of happening is 1. Okay, so the output, the desired output is a number in the range 0 to 1. So you might think, well, but isn't that just a subcase of regression? Yes, when you look just at the output. But the goal here is that the output should be interpretable as a probability. I'm going to use it as a probability of a heart attack, probability of a default. Okay, so unlike a credit level, which is just a number, okay, the probability of default is also a number, but it has a meaning, and you're going to use that meaning in order to do various things later on to make a decision. So, for example, you've told me the probability they will default, okay, and I'm going to use that somehow to decide what to do with them. Maybe I'll give them credit, maybe I won't, maybe I'll change the credit level, and so on and so forth. Okay. So when the desired output is not just a number between 0 and 1, but it should also be interpreted as a probability, we are going to call this logistic regression. Okay, and so three kinds of machine learning problems. We're going to discuss them in the context of linear models. Okay, and then you might say, well, why linear models? Aren't deep networks and this and that and so on and so forth the in thing for machine learning? Yeah, they may be the in thing, but for example, deep networks at their heart are made up of different components, and each component is sort of cascaded one on top of the other, and those components are linear models. Okay, so it's not that the linear model is not there, it's hidden. We call it a deep network. So in some sense, the linear model that we're going to discuss today, the linear model, okay, it's fundamental. And why is it fundamental? It's fundamental because A, on its own, it's a very powerful model. And I'm going to argue, I'm going to put my name on the line here, that if you cannot solve a problem, more or less, with the linear model, then odds are you haven't understood the problem that well. Okay? So I claim that pretty much any problem can be solved with enough thought. You think about the problem, you think about the nature of the task, you think about what are the inputs you're going to get. You should be able to solve it with a linear model. Okay? And we'll discuss exactly what I mean about that in the following lectures. Okay? And so if you can't solve it with a linear model, you haven't thought about this problem enough. Okay? So A, it's a fundamental model on its own, okay, and B, it's a fundamental model because it is the building block of other models. For example, deep networks are essentially cascaded linear models. Support vector machines are essentially a more robust version of linear models. Okay, so fundamental model. Okay. On its own, it's a fundamental model and also a building block for other models. Okay, so let us define the linear model first, and then we'll quickly cover classification. Okay, and in the rest of this lecture, we will cover regression and a particular application of regression to classification. And in a future lecture, we will address logistic regression. Okay, so the linear model starts with the linear signal. Okay, so the linear signal. Okay, so the linear signal, and let me just state it, and we've already seen it. The linear signal is, let me call it the signal S. Okay, is you have a weight vector W. So we have W transpose times X. This is the linear signal. Now, remember that both W and X belong to R to the D plus 1. Okay, so W is in R to the D plus 1, and X is in R to the D plus 1. Okay? And why? This is the augmented X. Actually, technically speaking, it's in 1 times R to the D. Okay? So it's the augmented X. Okay? Now, why is this called the linear signal? Well, there are two reasons why it's called the linear signal, and I'll tell you both of those reasons. Okay? And one of them is actually more important than the other. Okay, so it's linear in X. Okay, so that linearity in X, for example, when we talk about the perceptron, that linearity in X is what results in the separation between the +1 region and the -1 region being a line or a hyperplane. Okay, so this is what gives you the hyperplane. Okay, but look, so linear just means the power, the order of X in this signal is 1, but it's also linear in the weights. So linear in W, the weights. Okay. And that's the type of linear that we are really focusing on when we say linear signal, because this linear in the weights is what makes the algorithms go. Okay. So this is important for algorithms. And so typically when people say, oh, we're talking about the linear model, this is the linear that they're talking about. It's the linearity in the weights, W. In other words, the parameters that we can change in order to pick a final hypothesis affect the linear signal, well, linearly. And that makes the algorithms easy to develop and easy to implement and makes them work. Okay, for example, the perceptron learning algorithm. It's fundamentally reliant on the fact that we are linear in W. Okay. All right. So we have 3 kinds of machine learning problems, classification, regression, logistic regression. They are characterized by the type of the output and more mathematically by the set to which the output belongs. Okay. We're discussing this fundamental model, okay, which is called the linear model. And is it possible to perform all 3 of these tasks using the linear model, whose heart is really the linear signal? So the basic idea is the following. If we want to solve a different kind of machine learning problem, what we're going to do, we're going to take the linear signal and then transform it. Okay? So to solve different types of problem, okay, what do? We take the linear signal and transform it. Okay, and by transforming it in the appropriate way, we can produce an output of the type that we need for the different kind of problem. So we produce an output either y in plus or minus 1, y in the real numbers, or y in the interval 0 to 1. And the transformations are pretty easy. So pictorially, we have the linear signal S, which is W transpose X. Okay, we take it, okay, and depending on the type of problem we like to solve, okay, if we're solving classification, we transform it by just sending it through the sign function. Okay, so we send it through the sign function, which is minus 1, and then it goes to plus 1, and the jump is at 0. Okay, so this is the sign function. We send it to the sign function. The output is h of x is equal to sine of W transpose X. Wow, very simple. Okay? And that's exactly what we have been doing so far. And this we call the perceptron. Well, you know, if you transform it essentially using the identity transformation, okay, so the identity transformation, so you know, this is the transformation, you know, S H equals sine of S. This is the transformation H equals S. So it's just the identity transformation. You take the signal and pass it through the identity transformation, you get H of X is equal to W transpose X, and that's a real number. So you don't have to do anything to the linear signal if all you want is a real number. Okay, and this is the linear model for regression. The perceptron is the linear model for classification. Okay, and what about logistic regression? Well, very similar to the sign, except that rather than, you know, a transformation that takes you from minus 1 to plus 1, we want a transformation that sort of smoothly interpolates. So if this is 0, it smoothly interpolates from 0 to 1. Okay, it does something like that. That's typically called a sigmoid. So we will write that H is equal to some theta of S, where theta is this function. Okay, typically called a sigmoid. So this is typically called a sigmoid. Okay, and so the output H of X is theta of W transpose X equals. Okay, so I just want to show you, okay, without getting into too many details, okay, that with the linear signal as our starting point, we can easily transform the output in order to get the output that's relevant to each of the three kinds of machine learning problems: classification, regression, logistic regression. What we have focused on is classification. So let me just summarize classification, okay? And then we will address some issues with our current PLA, our current perceptron learning algorithm for classification, and then we'll move on to regression today. Okay, so let me erase. And we will be back.